Hello, my name is Jonathan Jenkins, and this is my presentation for ME5751 Robotic Motion Planning. In this presentation, I'll be talking about my truck simulator that we developed for this competition. So the objective of our project was to develop a truck-based motion planner. In our motion planner, we need to construct a collision-free path between some initial position and some goal position. In this motion planner, we also implemented truck kinematics to constrain the final output of the robot to simulate a realistic vehicle. Our project had 4 key requirements. First is to develop a potential map. Second is to develop a valid path using a path planner. Third is you implemented a P controller that would drive the robot. And lastly is to implement wheel kinematics and truck kinematics to constrain the final vehicle's motion. So we begin by developing our potential map. We take any given 500 by 500 pixel map and we convert it into a 500 by 500 matrix map. Using this matrix, we develop a occupancy map. This occupancy map identifies empty spaces white with occupied spaces black. As you can see in the image, this is the map that we will be using for our demonstration. Once we import a map to the motion planner, we use it to develop the potential map. Our potential map assigns a risk value to each empty space. This value depends on the distance away any unoccupied space is to an occupied space. The farther away an empty space is, the lower risk value it has. The closer it is to an occupied space, the higher risk value it has. An occupied space is given a value of 1,000. All unoccupied spaces within 15 grid spaces away from an occupied space falls within a zone that we identify as a safety zone. This is our inflation zone. The value assigned to every grid in the inflation zone is 850. Outside of the inflation zone, we have all the unoccupied spaces that we allow the robot to travel to. Their risk value varies from 800 at its highest down to 0. We use a linear equation to assign the specific value depending how far away each individual grid is from the occupied space. With our potential map done, we would then feed the information to our path planner. Our path planner decides which grid should the robot move to reach the final goal. We implemented an A-star algorithm, which combines a breadth first search BFS as well as a Draska's algorithm. A breadth first search algorithm assigns each grid a value corresponding to the distance away from the starting position. A BFS algorithm can identify the shortest distance away from any starting position to the goal position. Draska's algorithm assigns each grid a value corresponding to the distance away from the final goal position. Our A-star algorithm uses both a BFS search and a Draska's algorithm search. This finds an efficient path between the start and goal position. The A-star algorithm prioritizes searching grids with lowest risk towards the final goal position without the need to search the entire map. We also implemented a dual search A-star, starting from both the goal position and the final position simultaneously. With a dual search, the program can scan from 2 locations concurrently. Ideally, this will allow the program to locate the final path faster, using less iterations. In our implementation of the dual search A-star algorithm, we did see a drastic decrease on the number of iterations needed to find any given goal. Using a single search, it took this algorithm 32,561 iterations to find a final path to the goal. Using our dual search A-star algorithm, we reduced this number to 13,658 iterations to find a valid path to the goal. This is a reduction of 56%. The lower the amount of iterations, the more efficient the programming is, and the faster the algorithm can execute the commands. Now that we've completed our A-star algorithm and we've identified a valid path, we will send that data to our path planner. Our goal of the path planner is to segment this path into a set of waypoints. Each waypoint is to be given a set of theta values that will identify the direction of travel for the robot. Lastly, we will reduce the amount of waypoints in this path as much as we can to maximize efficiency of travel. However, we don't want to reduce this number too much because it will affect the accuracy of travel. So we begin by using the list of points given by the A-star algorithm and generating a list of waypoints. Each waypoint will be given a theta value depending on the direction of travel from that previous waypoint. As you can see in the map, each waypoint is represented by an arrow. The direction of the arrow represents the theta value assigned to each waypoint. As you can see, this path clearly shows the direction of travel the robot needs to take to reach the final position. After we generate the initial waypoint path, we then reduce the amount of waypoints in that path depending on the distance away between each two individual waypoints and the theta value between each two individual waypoints. The straighter the path, the less waypoints is necessary in that segment. The more complex the turn, the more waypoints we will allow to keep that complex turn with a high resolution. As you can see in the image, we reduce the waypoints significantly while keeping more waypoints on each individual turn. Once we have our path identified, we would then need to develop a controller. A controller is what is used to push the robot down the path. We implemented a P controller for our application. Our P controller was used to adjust the robot's linear and angular velocity. Adjusting the robot's linear and angular velocity, the P controller can guide the robot between each waypoint and eventually allow it to reach our desired final goal position. With a P controller implemented, we would then implement truck kinematics. A truck has a certain inherent kinematics based by its physical design. We use our kinematic model of the truck, specifying the car diameter, the car width, the car's axle distance, the wheel diameter, the steering angle, and even the speed limitations. And using these constraints, we can accurately constrain our simulation so that the robot moves in a very similar manner as a truck would. Taking out inherent vehicle constraints and incorporating the desired linear velocity and rotational velocity from the P controller. With this, we can limit the final vehicle's velocity and angular rotation in a very similar manner as a real truck. With the truck kinematics done and implemented with the P controller, we then have our final program ready to implement. Now it's time to move on to the demonstration. We develop a map to simulate a street. Our truck starts in the center of the map. It's tasked to move to the bottom left corner of the map. After running our algorithm, it found a valid path from the start location to our goal location in under 1 second. To find this final path, it took the algorithm 50,000 iterations. The number of points in the final path consists of 1,570 points. We converted 93 of these points to waypoints in our point tracker. From those 93 waypoints, we assign the theta values, and we further reduce the amount of points in this path down to 25. All of this took under 1 second to complete. Now the robot will begin its travel. As you can see, it moves very similar to a truck. It does not rotate in its place. It only takes curves along a maximum of 40 degrees steering angle. Its wheel velocity is limited to 20 rotations per second. As you can see, it will easily find its way from any starting position to any goal position as long as a valid path is there. We are quite happy with our robotic simulation. We believe the algorithm works pretty efficiently. It was able to complete every task in the competition and any map that we give it. Ideally, we want to implement a more advanced path planner and P controller for future development. As is, it works pretty well. This is the end of my presentation. Thank you very much.